When running experiments, you end up with measured values with experimental uncertainties, and you want to do calculations with those. You frequently want to know, well, what's my uncertainty on the result? So you can use significant figures, but it's not really enough if you want to be a little bit more thorough with this. So I'm going to show you a couple of ways here on how to do that. The first way here is using percent uncertainty. And so we've measured a small rectangular box. We've got 1.8 centimeters with a certain uncertainty in that measurement, 2.05 with a certain uncertainty, and 3.1 with a certain uncertainty. Those are the three measurements. We want to know what's the volume and what's the uncertainty on my volume. All right, so the calculation itself, hopefully we can do. We want a volume, you multiply the length times width times height. So we go 1.8. So we're ignoring the uncertainties at this point. We're just doing the calculation to start. And times 3.1. And then we get, as a result of that, 11.439 cubic centimeters, because we had 3 centimeters. Centimeters times centimeters times centimeters gives us cubic centimeters. Now we need to know how to report this. So using significant figures, you would just round this to 2 and call it 11. But we want to do a little bit better than that. So we're going to use percent uncertainty to propagate our error here. And in doing that, we're going to first find the percent uncertainty. And then we'll add it. And then that will give us the final percent uncertainty as sort of a worst case estimation here that we can multiply by our calculated number to get our final experimental uncertainty. So let's find the percent uncertainties from the 1.8 plus or minus 0.01 centimeter figure. We take the uncertainty 0.01 centimeters. We divide by the measurement 1.8 centimeters, and we multiply by 100, and we end up with 0.556%. So I'm just keeping some extra digits here as we go along to not introduce round-off error. And then we do the same thing for the other two measurements. So 2.05 plus or minus 0.02 centimeters. Again, we put the uncertainty on the top and the measured quantity on the bottom, multiply by 100% to get it as a percentage, and we end up with 0.976%. So these are both under a percent error, which is pretty good. And then here, 3.1 plus or minus 0.1 centimeters. Here will probably be over a percent error, it looks like. 0.1 centimeters over 3.1 centimeters times 100% gives us 3.226%. So we've got our percent uncertainties, and now we'll add those together. So we get the 0.556% plus 0.976% plus 3.226%. And that gives us a resulting percent uncertainty on our calculated value, 4.758%. We can now multiply by the calculated number in order to get the uncertainty on our calculation. So the calculated number is that 11.439. Again, I'm not rounding anything yet. Then we multiply by my percent uncertainty, 4.758%. Make sure you use the percentage on this so that this ends up correct. And then you end up with 0.5442 cubic centimeters. So since this is an uncertainty, we don't want to keep all the digits here. I generally will keep 1, maybe 2 digits. Here I'm going to keep 1. And so we'll keep 1 digit here and say my uncertainty is plus or minus 0.5 cubic centimeters. So we can come back to this number and we can write our final result as that number, and we round it to the digit where that is. So here we're rounding it to this 10th place, 11.4. It's got a 3 after, so we round down to the 11.4. And then this will be plus or minus 0.5 with units of cubic centimeters. If I can actually write plus or minus symbol. And there we have our calculated value with an experimental uncertainty. So that's one way of propagating experimental uncertainty by using percent uncertainty. Another way is we can use some rules. So you can look up rules for error propagation. And here's one. So here's the rule. The rule says that when we multiply things like this, you take the error divided by the absolute value of the measured quantity, and your resulting error divided by the quantity, so this is the fractional error essentially, is going to be the square root of each individual uncertainty divided by the measured quantity squared. So, and you can do this with percent uncertainties as well. This is just, percent uncertainties, it's just everything's multiplied by 100. So you just end up with 100%. The difference here is, rather than what we did previously, is we just added them. So this we just added. Here, we're going to be adding them in quadrature, right? So this squaring them and then adding them and then taking the square root. And what this does is, this is a little bit more appropriate if this error is, as we would expect, random, non-biased, normally distributed error. Then on average, when you have something that maybe it's a little high and some measurement that's a little low, you wouldn't expect that everything would be high, right? So on average, you wouldn't expect that worst case scenario of just adding together the uncertainty. You'd expect that you would average a little bit lower there. And so this is one way of doing that. And this is true for when your calculated quantity is a result of, multiplying and dividing by whatever. So this is multiplication and division here. So here you would take square root of the 0.01 over 1.8. We know the dimensions are going to cancel out since they're the same units here. Plus 0.02 over 2.05 squared plus 0.1 over 3.1 squared. So you add those together, or you do the divisions, square them, add them, take the square root, and you end up with a number coming out. So this is a fractional number, right? This is 0.034159. So that's a fractional uncertainty. If you want the percent uncertainty, again, you can just multiply by 100%, right? And so you would end up with, just to tell you, that would be 3.416%. So now this is different than what we did before. Before we had 4.758% as sort of our worst case scenario. This is like a more realistic scenario here. And in this case, we now take and do the same thing with this, where we can multiply our calculated quantity, which is still 11.439 cubic centimeters, by that percent uncertainty, 3.416%. And we end up with our new experimental uncertainty, plus or minus of 0.391 cubic centimeters. And now this, again, we round probably to one digit here, and then we'll round this to the same digit, whatever we round the other one to. And so here we'll get 11.4 plus or minus 0.4 cubic centimeters. And that's very similar to what we did before, right? Before we got 11.4 plus or minus 0.5. Here it's plus or minus 0.4. So very similar, but notice this is slightly less experimental uncertainty, and that's because if the errors are randomly distributed, when you're multiplying them here, you wouldn't anticipate that everything would be on that worst case scenario there. So those are a couple of different ways of propagating around the error, and that's generally what I'd recommend in any sort of actual experimental situation, is using one of these techniques. in order to propagate around your error and get accurate ideas of what your actual experimental precision is on those calculated values.